to write. So for the fourth period, now we're into the 4s1 for potassium here. And what we notice when we get to the third element in the fourth period is that we go 4s2, and then we're back to the 3ds. So if you look at the energy diagram, what we see is that the 4s orbitals are actually just a teeny bit lower in energy. They're just ever so slightly lower in energy than the 3d orbitals. You can see that as you fill up your periodic table. It's very clear, but also we'll tell you a mnemonic device to keep that in mind so you always remember and get the orbital energy straight. But it just turns out that the 4s is so low in energy that it actually surpasses the 3d, because we know the 3d is going to be pretty high in terms of the 3 shell, and the 4s is going to be the lowest in terms of the 4 shell, and it turns out that we need to fill up the 4s before we fill in the 3d. And we can do that just going along, 3d, 1, 2, 3, and the problem comes when we get to chromium here, which is instead of what we would expect, we might expect to see 4s2, 3d4. What we see is that instead it's 4s1 and 3d5. So this is the first exception that you need to know to the Aufbau principle. The reason this is an exception is because it turns out that half-filled d orbitals are more stable than we could even predict. You wouldn't be expected to be able to guess that this would happen, because using any kind of simple theory, we would in fact predict that this would not be the case. But what we find experimentally is that it's more stable to have a half-full d orbital than to have a 4s2 and a 3d4. So you're going to need to remember, so this is an exception you have to memorize. Another exception in the fourth period is in copper here. We see that again, we have 4s1 instead of 4s2. This is 4s1, 3d10. We might expect 4s2, 3d9. But again, this exception comes out of experimental observation, which is the fact that full d orbitals also are lower in energy than we could theoretically predict using simple calculations. So again, you need to memorize these two exceptions. And the exception in general is that filled d10 or half-filled d5 orbitals are lower in energy than would be expected. So we get this flip-flop where if we can get to that half-filled orbital by only removing one s electron, then we're going to do it. And the same with the filled d orbital. And actually, when we get to the fifth period of the periodic table, that again takes place. So when you get to a half-filled or a filled d orbital, again, you want to do it. So those exceptions would be with molybdenum and silver, would be the corresponding elements in the fifth period, where you're going to see the same case here, where it's lower in energy to have the half-filled or the filled d orbitals. So here's the mnemonic I mentioned for writing the electron configuration and getting those orbital energies in the right order. All you do is just write out all the orbitals, the 1s, then the 2s, 2p, 3s, 3p, 3d. Just write them in a straight line like this. And then if you draw diagonals down them, what you'll get is the correct order in terms of orbital energies. So if we go down the diagonal, we start with 1s, then we get 2s, then 2p and 3s, then 3p and 4s, and then that's how we see here that 4s is actually lower in energy than 3d, then 4p, 5s, and so on. So if you want to on an exam, you can just write this down quickly at the beginning and refer to it as you're filling up your electron configurations. But also, if you look at the periodic table, it's very clear as you try to fill it up that way, the same order comes out of that. So whichever works best for you, you can do in terms of figuring out electron configurations.